Hey friends, it has been again. Hey friends, it's been again. Um, this is a video meant to be a replacement for the class we missed on January 26th, I suppose it was. And I'm just trying to cover the material that we didn't get to because for obvious reasons. Okay. So your assignment with regard to what to do for the class is to follow along and take what notes you can, and of course, upload notes um, as soon as you practically can. All right, cool. Okay, so the thing that we are finishing up there is this section 3.2, which was talking about measures of dispersion. And the main thing that was new that we were getting from that was this idea of a standard deviation. So, with regard to standard deviation, we are going to have a connection to what it tells us about a data set. Okay. Let me see if I can go ahead and share screen with y'all. And, hmm, and I'm going to try to do it where I'm going to do it with just the content. I was going to try to do it where I was in the foreground, but I am afraid I will end up having my head being in the way of the actual content. So here we have something that's referred to as the empirical rule. And the empirical rule is an observation about data which happens to be normally distributed. What do I mean by normally distributed? I mean that if you make one of those histograms and make a lot of little bars with it, it will tend to have this sort of shape here, where it is tall in the middle, small on both ends, and roughly symmetrical. Okay. So what we find for the empirical rule is that if you have data that is normally distributed, that you will find 68% of that data will fall between plus and minus one standard deviation from the norm. 95% will fall between plus and minus two standard deviations from the norm. And 99.7, practically all of it, will be within three standard deviations of the norm. So the thing that we're going to think about here is if we have X is normally distributed, I'm going to abbreviate that, with the mu, the mean being 100, and the sigma, the standard deviation being, what was it, 15. And we're going to figure out a few different situations that go on here. So the first situation for us to figure out, that's not just reading it right off the graph, is saying what happens, what percent of the population is between 100 and 115. Well, remembering that we just said that the mu is 100, that's going to put the 100 at the center. And since we've got 68% in the middle and um, the population is symmetrical, that means that here we're going to get 34% of the population being between 100 and 115. Okay. So then here we ask, well, what percent of the population is between 85 and 130? Remembering again that the center is 100. Well, 85 is one standard deviation below, and 115 is one standard deviation above. Well, that means two standard deviations above would be this 130. Okay. So if you go ahead and take this half there, you have the 34% plus if you take this half here, well, that's going to be, what is half of 95? 47.5%. So that means when you add those together, you'll get, let's see, 81.5% by taking those two halves, okay? So any of these questions where it's a multiple of 15 going up or down, you're going to be able to split the difference and figure out these sorts of things. So here on this one, we ask, well, what percent of the population is below 70? Well, remember that 70 would be 2 standard deviations below. So it would start here. And so this would be what is in this half of the stuff that's not in the middle. Well, if the middle is 95%, then the two ends are 5%, but we only have one end. So we'd say about 2.5% of the population's below that, okay? Same sort of idea happens with this one here, except it's on the upper end. And so that one is also going to be about 2.5% of the population's up there. And then this last one here has us thinking, what if we talk about less than or equal to 55? Well, the middle is 100. And so 3 standard deviations below, that's 45 units below, is going to be this part. And then 3 standard deviations above is going to be this part here. So the part that's outside of the middle 99.7 together is going to be 0.3%. So a very small part of the population is going to be outside of those. All right. Then we're going to pop over here and talk about something called Chebyshev's theorem. So Chebyshev's theorem is something where it doesn't have to be a normally distributed population. Really, truthfully, Chebyshev's theorem is just kind of a neat coincidence about how some of the algebra for figuring out data comes through, okay? So what we find is if we talk about, where did I put that at? If we talk about a certain number of standard deviations, I should have made that bigger, a certain number of standard deviations above or below the mean, okay? So the proportion of the population that is within those, however many standard deviations, is going to be at least 1 minus 1 over k squared. That's not saying it will be exactly that amount, okay? Or that it can't be more, but it'll be at least that. So the interval that we'll talk about on this is always going to take the middle, the mu, and say plus or minus that k times whatever the standard deviation is. All right, so let's look at our example here. It says the average household income in Greensboro is about $45,000. This data is out of date, but I looked it up sometime before the pandemic, and I've been using it still. And then the standard deviation is $10,000. That's not true. I can't find the data about standard deviation anywhere, so I just made up a number, okay? So without any information about the shape of the distribution, that's our key that tells us when to use Chebyshev's theorem, is when you have no idea about the shape of the distribution. You don't know it's normal, okay? What is the maximum proportion of households with an income below $15,000? Okay, so the thing we're going to do with that is to take the $15,000 and the $45,000 and subtract to get $30,000 And then we're going to say, well, how many standard deviations is that? So that's K times the standard deviation is 10,000. That tells me that the K has got to be 3. And then we plug into the Chebyshev formula and say 1 minus 1 over K, that's 3 squared. So 1 minus 1/9 is going to end up being 0.8889. Okay. That will be the proportion that is at least that close. So then, let's see, that would be going from, where was it? 15,000 to, let's see, what would be 45 plus? So that'd be 75,000. So about 89% of the population is between 15,000 and 75,000. So that means outside would be 1 minus 0.8889, which will turn out to be 0.1111. Is that right? I think that's right. Okay. But remember that we didn't say that we just wanted it outside. We, in fact, wanted it below. Okay. So assuming that you've got some symmetry, take that 0.1111 in half, and you end up with oh gosh, I should be embarrassed about the fact that I'm having trouble doing that in my head, but I'm going to slip out a calculator here real quick. Where's my calculator? And say 0.1111 divided by 2, and I get 0.05555. Well, let's round it to 6. So that's about 5.6% of the population. So no more than 5.6% of the population is dealing with an income below 15,000, according to our data. Okay. All right. So now let's talk about measures of position. So when we talk about measures of position, the one you've probably heard about is percentiles. Here in a second, we're going to talk about quartiles, but percentiles, the thing that people have usually heard of. So when we talk about percentiles, they need to break the population up into 100 pieces. And because they're breaking the population up into 100 pieces, that means there's going to be 99 of them. So we really only talk about the first percentile, the second percentile, the third percentile, etc., up to the 99th percentile. We don't really say anything about the 0th percentile or the 100th percentile. Okay, those are just not terms that we use. But when we talk about a percentile and we give it a number, that number is meant to represent that that percent of the data is either equal or less. Now, realize that this does lead to there being a little bit of ambiguity, especially when you've got scores that are repeated. And if I remember right, this example purposely points up that sort of confusion, right? So first thing on this one here, since it's asking us, this data is representing average posts on X per day for 12 students. We know that we've got n equals 12 that we're dealing with out of our data here, okay? And then it says, what percentile is the score 8.6? So you're going to look in here and say that 8.6 appears in 2 positions, and we're going to think about it being the second position, because since this is talking about the amount of data that can be the same or less, then we always have to think about the later position of it, okay? So then our percentile, we will talk about the position that it's sitting in the sorted data. So fourth out of those 12 pieces of data. And so since that gets us 0.333 repeating, then we would report back that this is the 33rd percentile. Okay. And that's what there is to it. You find the position, divide it by how many there are, and then round it as close as you can. Okay. Then this next part asks us what score is the 25th percentile. So with the 25th percentile, we'll have to think about 0.25, and we're going to multiply that by our 12 in order to figure out our position. And then doing that, we end up with 3 out of that. And then for the third position, we look back in here and we say, oh, that's the 8.6. So 8.6 occupies the 25th percentile, which is not what we expect to have because that was also the 33rd percentile. So I just want to point up that this thing of talking about the 25th and the 33rd percentile is confusing because when you have a repetition in the data, it doesn't really fit quite our setup for thinking about percentiles. Okay, so I realize this answer is kind of confusing, and that's on purpose, right? The 90th percentile will probably turn out a little bit nicer. So here we'll have to take the 0.9, multiply that by the 12, and when you do that, you get, oh shoot, wow, super embarrassing. 0.9 times 12. Yeah, 10.8. That's what I thought it was. So 10.8, which of course isn't an actual position. So you have to round it to the closest one and look for what's in the 11th position. And then we'll go back up here and say that 13.4 is at the 90th percentile. Okay, that's it. That's what we're going to do with percentiles. Okay, this part here, we have to talk about something that's called a box plot. So in order to talk about a box plot, we are going to have to talk about a few terms here. So far, we know what the median is. And if you recall, we labeled that to be Q2. Okay, so our median is going to divide the population into an upper half and a lower half, okay? And the median itself doesn't really lie in either one of those. But then what you will do to find something called Q1, which is the first quartile, is to find the median of the lower half. And you can probably guess that Q3 is going to be the median of the upper half. Okay, so those numbers, Q1, Q2, and Q3, are going to form a box that we're going to put above our number line. Then we're going to think about the minimum and the maximum, and we're going to mark those off as well. And we're going to draw whiskers out to that. If that's a bunch of terminology that you're not used to, don't worry, we're going to get it as we go. All right. So what we have to look about here is to figure out where these numbers lie. So first thing we're going to have to do is to sort our data. Oh goodness, look, some kind soul sorted our data for us. Wasn't he nice? Okay, then we have to count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's 13 data points. And that means that I'm going to be able to get the middle score, 1, 2, 3, 4, 5, 6, 7. So the seventh one is going to be here, and that's what we refer to as our median, our Q2. Okay. Now in the lower half down here, obviously we know what our minimum is. So I'm just going to label that real quick to be our minimum. But then for this lower half, we'll have to say there's 1, 2, 3, 4, 5, 6 things in it. Since there's 6 things, that's even. And we're going to talk about these middle 2 here, right? And so you take those middle 2 and average them to figure out what that median is. So what is that? 10,960 plus 11,445, and divide that by 2, and you get 11,202.5. So I'm going to write this here. Q1 equals 11,202.5. Okay. And then likewise, when we're looking up here at the upper half, we'll say 1, 2, 3, and then we'll put those 2 in there. So 15, 635 plus 15,750, and then divide by 2, and we're going to get that right in here. Q3 is equal to 15,692.5. And of course, this will be our max here at the 18,865. Okay, so what we're going to have to do now on the number line is to look across here and roughly place our Q1 and our Q3, well, sorry, our Q1, Q2, and our Q3. And we're just going to make little vertical lines to indicate those. So 11,202, let's see, that seems like that's going to be somewhere around here. So right about here, I'm going to make a vertical line. And then 14,780 be roughly here. And then for this 15,692-ish, that'll be roughly here. And then we're trying to make a box out of these. My box isn't going to be all that great. Sorry about that. Yeah. Okay. And I'm going to go ahead and jot down on this the 11,202.50, the 14,780, and the 15,692.5. Okay, now we got to get our max and our minimum in here. Our minimum is 6,450, so that's going to be pretty close to the 6,000. And then we draw the whisker in to connect those. That's supposed to be longer. And then the 18,800 and something, that's going to be pretty close to the 20,000. We draw a whisker in to connect those. Nope. Computers don't want to be my friend right now. Okay. And that is a box plot. All right. Now you'll notice that there is this phrase here about, are there any outliers? So to talk about outliers, we're going to have to calculate something. And I'm going to have to add an extra page in here to do this. But I'm going to write down here a number called IQR. That is your interquartile range. And it is just going to be Q3 minus Q1. And so we're going to have to take 15,692.5 and subtract from that 11,202.5, and we will get 4490. Okay, so the IQR plays a fairly similar role to what standard deviation does. It's not the same thing, but it plays a similar role. Hope that makes sense. So in my extra page that I've got here, or that I'm about to put in here, oops, actually, I think I'm going to take and copy this. Okay, I only want to copy this, not the extra stuff. Copy, add a page, paste, and it decided to copy more than I wanted. All right, so your IQR is that there, all right? So what we do is to construct these things called an upper and lower fence. Okay. And so for your upper fence, you will take Q3 and add 1.5 times the IQR. Okay. Anything that is outside the upper fence is going to be an outlier. Okay. So our Q3 was, oh, shoot, I've forgotten already. I'm sorry. 15,692.5. 15,692.5 plus 1.5 times is 4490. So I will just have to do a calculator with that. 1.5 plus 5. I got 22,427.5. Okay. So nothing above this. If you don't believe me, go back and check. The highest value was 18,865. So nothing is above that, meaning there's no outliers on the upper end. Okay. Then on the lower fence, for that, you need to take Q1 minus 1.5 times the IQR. Okay. So then for that, I had to go back and see what was that. 11,202.5 minus 1.5 times the 4490. So this time, 11,202.5 minus 1.5 times the 4490 turns out to be 4467.5. Okay. And if we go back and see, our minimum that we had here was 6450, 18,865. Since the minimum was not outside of that fence, there is nothing below this. And that means that there are no outliers in this data. So what's that mean? Well, an outlier, as you'll see in the reading, is just going to be data that doesn't seem to belong with the rest of the data. So if, for instance, I gave an exam sometime and everybody in the class got scores that were somewhere in the 80% sort of range, and then one person got 110, that person is an outlier because they don't fit with the rest of the data. So this gives us a way to determine whether whether a score is an outlier or not, based on this idea of a box plot. If you have outliers in your box plot, the thing that they will represent them with is an asterisk that is on past the end of the tail there. I would like to suggest you all to read the section carefully about how they construct box plots. Nobody ever constructs box plots by hand, but they will tell you exactly how to do it. So, all right. All right, so here we have an example here on example 3 of some data that actually has an outlier with it. And this particular piece of software represents our outliers with circles instead of asterisks. But like I say, some software will use an asterisk instead. So This asks us to compare the box plots and describe. I believe this was actually gas mileage, so miles per gallon from two different models of cars, two different models of car from the same manufacturer. And so with model number one here, we can see that the median that we had was about 12.5 miles per gallon, whereas with this car here, the median was about 7.5 miles per gallon. Okay. And then other things that we can tell on this is the middle scores, the ones in the interquartile sort of range there on the first population is pretty narrow. And then it has some outliers, whereas this population had a very broad IQR. So when we're asked here to compare the box plots and describe, then we would say that population one has a higher median MPG, but has outliers above and below. Okay. Whereas you might also make a note that population 2 is more symmetric. Okay. But so basically, when you have two box plots given to you like this, you are generally speaking going to take a quick look and compare the populations. Usually, you first notice which one has the higher and lower median. And then you can take a note here that most of the box for population 1 lies above the box for population 2. And that suggests that population 1, whatever model of car that was, probably has a significantly higher fuel efficiency than model 2. Okay. So that's what we do with that. And then, okay. Our next bit here is looking at in a population with the height. I don't remember what the question asks. In a population with height, mu equals 68 inches and sigma equals 2.5 inches. If I remember correctly, that was around 2015 or 2020. That was the average height for American males, and the standard deviation, I think, is right, but I might not be right. So this asks us to figure out what is the standard score of a person who is 6.1 inches tall. All we mean by standard score is what you may have heard elsewhere referred to as a z-score. And to calculate a z-score, you take your score that you're given, your raw score, subtract your mu, and divide by your sigma. So here we've got the person who's 61 inches tall. We subtract the average 68, and then we divide by the 2.5 for the standard deviation. So you have -7 divided by 2.5. Yeah, I can't do that in my head. So I grabbed a calculator here and I got -2.8. Okay. It is a unitless thing. It is just giving the answer to the question, how many standard deviations above if it's positive or below if it's negative is that data score. Okay. Then example 5 says the SAT math is standardized with the mu being 500 and the sigma being 150. Okay, so I'm going to jot down over here SAT mu is 500 and the sigma is 150. The ACT is also standardized, and for that, the mu is 21 and the sigma is 5.5. Okay. So in this situation, you're thinking about somebody who's preparing to apply for college, and they've taken both tests and they've gotten their scores on them, and they want to figure out which one to submit to Guilford College in order to make the best impression and maybe qualify for some scholarships or something. So you figure out the z-score for each one of these. So for the SAT, they got a 730. You subtract the 500 and divide that by 150. And so when you do that, you get positive 1.53, and then the 3 repeats. Okay. Then for the ACT, we're going to take their score of a 32 minus the 21 and divide it by 5.5, which, oh, for once, will be one that I don't need a calculator to do. So 11 divided by 5.5 turns out even, and so it's 2. Since the 2 is a better score than the 1.533, that suggests that when they want to submit when they want to submit the scores to the college, they want to submit their ACT to make a better impression. So, yay. Y'all feel good with that? All right. Last one here. So this is actually relating back to something that I actually did in college. I worked at a job in a factory where we were producing these plastic moldings. And when the manufacturing process means that there will be some variation that happens. And they set up what is referred to as a statistical process control to try to automate and decide how or which parts were allowed to pass on and be used, and which ones were actually going to cause some sort of problem because they were too much out of the standard. So here, this manufacturer is producing plastic moldings, and the length on them is going to have an average of 45 centimeters and standard deviation of 8.5 centimeters. So then we're going to try to figure out if we don't want it to be more than 1.5 standard deviations above or below the mean, then what is the range of lengths that we actually allow for the plastic moldings? Okay. So then to do that, all you're going to have to do is to take your 45 plus or minus the 1.5 times the 8.5. Okay. So that is 45 plus or minus 12.75, which is going to be, if you subtract, that will end up being 32.25 centimeters. And when you add, it's going to be 57.75 centimeters. Okay. So when somebody is sitting on the production line there, they'll have a little measuring device that they will check the length of these moldings out on. And if it's 60 centimeters or more, they have to toss it out. If it's 32 centimeters or less, they have to toss it out. So they're only allowed to accept things that are between those two measurements. Okay. And I believe, yep, that is the end of these. So I'm going to stop mirroring and stop sharing and jump back here and say, that is the information about chapter 3. You should be in good enough shape to tackle all the stuff that we have for the chapter 3 homework. And I will hopefully see you in class on Wednesday. Fingers crossed.